Good morning, everyone. Thanks for the introduction, Vijay. I'm excited today to talk about PipeDream, a new way to parallelize DNN training over multiple accelerators. This is joint work with awesome folks at Carnegie Mellon, Microsoft Research, and Stanford. Deep neural networks have empowered state-of-the-art results across a broad range of applications, like image classification, machine translation, speech-to-text, and game playing. However, deep neural networks first need to be trained before they can be deployed in end applications. At a high level, training a DNN model involves finding weight parameters W that fit a training data set, consisting of examples and associated labels. During the training process, an input sample is passed through the model, generating intermediate outputs called activations and a prediction that might be incorrect. Errors between the prediction and the true labels are backpropagated back through the model, generating gradients and weight updates. These weight updates can then be used to update the latest weight parameters. In order to be able to train a model, a large number of iterations like this need to be performed. And this is extremely time and compute intensive. In order to obtain trained models in a more reasonable time frame, people have resorted to parallelizing over multiple accelerators. One common way of doing this is data parallelism, where every worker has a copy of the model. Inputs are sharded, weight updates are generated independently on each worker, and then these are aggregated periodically using communication collectives like all-reduce. However, we observed that this communication overhead is often fairly high in public cloud deployments. So in this graph, I'm going to show the percentage of time spent in communication on the y-axis and the number of GPUs on the x-axis. And we're using 8 GPU servers here on Amazon AWS. We observe for 3 different models, the communication overhead is often as high as 80%. Note that the ResNet 50 model here scales better because it has compact weight representations, which allow it to scale more gracefully for data parallelism. Another problem with data parallelism is that it doesn't quite work if your model doesn't fit on a single worker. To resolve this issue, people use model parallelism, where a single version of the weights are split over the available workers. And now, instead of having to do an expensive all-reduce communication call, you can actually just do peer-to-peer communication across the different workers of these intermediate activations and gradients. The problem with model parallelism, however, is that it has low hardware efficiency out of the box. This is a timeline of what a model parallel execution might look like. On the y-axis, we show per worker execution, and on the x-axis, we show time. Each box shows what that worker was doing at that particular, in that particular time unit. Blue boxes show the forward pass, green boxes show the backward pass, and the hashed boxes are idle periods. And the numbers in the boxes indicate the ID of the input that's flowing through the system at the current point in time. We observe that at most one worker in this setup is active at any point in time. In order to solve these issues, we propose pipeline parallelism, a combination of data and model parallelism with pipelining. The timeline figure now looks like this, where we have multiple inputs injected into the pipeline at any point in time. This ensures that in steady state, all of our workers are going to be active, and there are no idle periods. Note that the total amount of time spent in steady state far exceeds the total amount of time spent in the startup phase. Pipeline parallel training is able to accelerate training by up to 5.3x compared to existing methods like data parallelism without sacrificing on the final accuracy of the model. Even though pipelining is a common optimization used in systems such as in your CPU processor, pipelining in DNN training has some unique challenges. The first challenge is how should we assign operators in the DNN model into pipeline stages? This is particularly challenging because each operator consumes a different amount of computation time, and activations and gradients need to be communicated across these different stages, and different operators in the model have different sizes for these. Second, training is bidirectional, as I alluded to earlier in this talk. So you have a forward pass followed by a backward pass to compute gradients. And so the natural question that falls out of this is, how should forward and backward passes for different inputs be scheduled? And the final challenge that I'll talk about today is backward pass operators in the DNN model are stateful. That is, they depend on some internal state. That is, the weight activation, the current weight parameters, as well as activations that you computed in the forward pass. And the natural question that falls out of this is, how should weight and activation versions be managed so that the final model we train is high quality? For the rest of this talk, I'm going to delve into these challenges deeper and also describe how PipeDream addresses these challenges. At a high level, assigning operators to pipeline stages involves figuring out where to chop your model across the different workers. So here, let's assume that we have a model with 12 operators, and we're trying to split it over 3 workers. In other words, we're trying to create 3 stages. Now, if each of these stages take times T1, T2, and T3, one desired property we want from our partitioning is that T1, T2, and T3 are as close to each other as possible. This ensures that compute resources are seldom idle, leading to better hardware efficiency. In addition, we need to communicate activations and gradients between different stages, and this takes some time. So another desired property we want from our partitioning is that this communication time is as small as possible. Because the less time we spend communicating, the better the hardware efficiency of our pipeline setup. However, we observed in practice that merely splitting operators over the available workers doesn't always give us a good pipeline setup. Consider a simple model with just 2 operators. Let's assume that the first operator takes a compute time of 2 time units, and the second takes a compute time of a single time unit. Now it's easy to see that the second stage here can process inputs at roughly double the rate of the first stage. What this means is that the second worker is going to spend a lot of time waiting on the first worker to complete its processing in steady state. To resolve this problem, we can replicate the first stage. This ensures that the first stage is able to process inputs at roughly the same rate as the second stage, which gives us good load balancing across stages. Another nice property of stage replication is that in some cases, for some operators, the amount you would communicate doing data parallel updates is much smaller than the size of the intermediate activations and gradients. So for these particular operator subsets in your entire model, data parallel communication is cheaper than the alternative. The upshot of all of this is that stage replication can help us load balance computation better and reduce communication between workers. This is an example PipeDream configuration. In this particular example, we have 4 stages, and each of these stages have different replication factors. We represent a PipeDream configuration by the replication factors of each stages. So in this particular case, since we have 4 stages, we have 4 different numbers, and we call this 2, 3, 2, 1. PipeDream is able to partition operators amongst the different workers while also deciding on the appropriate replication factors using a profiler and a runtime. PipeDream's using a profiler and an optimizer. PipeDream's optimizer is able to generalize along many different axes. One particular axis of interest is hardware topology. In practice, people train DNN models using multi-GPU servers, where communication bandwidth between GPUs on the same server is much higher than communication bandwidth across servers. PipeDream's optimizer is also able to generalize along different model structures and also is able to incorporate other constraints such as memory capacities of the workers. And we have details on how we actually do this in our paper. The second challenge PipeDream needs to deal with is determining how to schedule forward and backward passes of different inputs. PipeDream handles this using a scheduling discipline which we call 1F, 1B. Workers are always alternating between forward and backward passes. This ensures that workers are always utilized, and gradients are used to update the model immediately. As before, in steady state, we see that there are no idle periods. And we see for every worker, it's alternating between forward and backward passes. So for example, worker 1, first there's the forward pass for input 5, the backward pass for input 2, the forward pass for input 6, and so on. In order to be able to support stage replication, we need to modify this mechanism slightly, and our paper has more details on how we do this. The final challenge that PipeDream needs to address is it needs to manage weight and activation versions in an intelligent way to ensure that the final model is high quality. The reason we need to do this intelligently is because naive pipelining leads to a mismatch in weight versions. Consider some input x sub n that's moving through the pipeline. Let's say that it uses some weight version w sub n on a particular worker and generates an output y sub n in the forward pass. Now, as other in-flight inputs complete their backward passes, this weight version gets updated. So let's assume that by the time we're ready to do the backward pass for this same input, the weight version has advanced to some w sub n plus p. Now, this is problematic because input n sees updates in the backward pass that it didn't see in the forward pass, which leads to incorrect gradient computations in the backward pass. To solve this problem, PipeDream uses a weight stashing mechanism where it stores multiple weight and activation versions to ensure that the same weight versions are used in both the forward and the backward passes for a particular input. So now, when we complete the backward pass for input n, we use the same weight version that we used in the corresponding forward pass. This also has a nice property that the worst case memory footprint is similar to data parallelism, because even though we're storing more versions of weights and activations, each of these are smaller because the model is actually, the operators in the model are split over many workers. To conclude, I'm going to present some empirical results on how PipeDream does to other comparable approaches. However, due to time constraints, I'm not going to be able to address all of these, and I encourage you to look at the paper to see other empirical results. Some notes about evaluation setup. We integrated PipeDream with PyTorch in about 3,000 lines of code. We use PyTorch's communication libraries for inter-worker communication. We use the Nickel backend for data parallelism baselines because Nickel is explicitly optimized for all reduce, and we use the Glue backend for PipeDream's communication. And we ran experiments on 3 different server types, 2 server types in the public cloud on Azure and AWS. In particular, cluster B is run on 8 GPU servers with NVIDIA's proprietary NVLink interconnects. And this provides extremely high bandwidth between GPUs on the same server. So to present some results, I'm going to show essentially PipeDream compared to data parallelism while training a VGG16 image classification model. I'm showing top 1 accuracy on the y-axis and time on the x-axis, and up and to the left is better. Basically, you want to train high-quality models faster, so in less time. This is what the results look like. So PipeDream is able to train models up to 5.3x faster than data parallelism. We have other results similar to this in the paper that span many different tasks and models. In particular, we evaluate PipeDream on 4 different tasks: image classification, translation, language modeling, and video captioning. And we show that with the same number of GPUs, PipeDream is able to go up to 5.3x faster than data parallelism. In addition, we observed that PipeDream's optimizer recommends a large number of different configurations, such as 15.1 straight, which is essentially a pipeline with no stage replication, and even a fully data parallel setup for ResNet 50, which has extremely compact weights, where data parallelism actually scales fairly gracefully. And PipeDream is able to do this completely in an automated fashion. The reason for PipeDream speedups is it's able to reduce the amount of communication across different workers. In this particular graph, I'm showing the number of bytes communicated per training sample on the y-axis for different models. And we see that the activations and gradients that you send in a non-data parallel setup, that is like for example, a straight pipeline, is often up to an order of magnitude smaller than the amount you would communicate with data parallelism. We see that this holds for other models as well. So GNMT8 is a machine translation model, but we see that this is true for other machine translation models as well as image classification models. ResNet-50, as before, we see that the data parallel, the amount you communicate with data parallelism is less, which is why PipeDream's optimizer automatically recommends data parallelism for that particular model. So to conclude, model and data parallelism often suffer from high communication overhead and low resource utilization for certain models and deployments. PipeDream shows that pipelining can be used to accelerate DNN training and is able to achieve speedups of up to 5.3x. PipeDream is open source at that URL, and with that, I'm happy to take questions.
Hi there, great work. Petros Mañares from Google. A lot of the results that you showed show models that are very sequential, very stacked. I guess ResNet has some residual connections. But I could imagine situations where you have very complex data flow. How do you deal with pipelining when you have multiple stages to finish before the next one starts?
Yeah, so that's a good question. The question was, how do we deal with models that are not completely sequential, that are like more branched, for example? So the answer to that is essentially PipeDream needs to send like multiple it might need to receive multiple activations from multiple different machines. PipeDream's essentially the way we engineered this, it was able to handle that fairly gracefully. However, we observed that in most of the models we looked at, the models were fairly sequential, and this is true for even models like BERT, etc. But essentially, PipeDream, each of the stages can receive intermediate activations from any other previous stage, and so that's not necessarily fundamentally problematic.
Good, thank you.
Yep.
Gennady Pichimenko, University of Toronto.
Yeah.
So my question is a great work. So my question is about a memory footprint overhead. So you mentioned that one of the big motivations for essentially pipeline parallelism is to reduce the memory footprint. So sometimes model doesn't fit. But your approach, PipeDream, also increases the memory footprint.
Yeah, so that's a good question. The question is about memory footprint. So the purpose of this work was to try to essentially augment model parallelism, combine it with data parallelism, and see if we can get performance speedups. So we were trying to use model parallelism to get better performance. It is true that model parallelism was originally conceived to train super large models that don't fit on a single worker. We are looking at ways to reduce the memory footprint. So PipeDream's memory footprint is no worse than existing approaches like data parallelism, but we are looking to decrease the memory footprint so that we can deploy PipeDream in settings where the model doesn't fit on a single worker too. Yeah.
Okay, thank you.
Of time, so let's have one more question and then we'll go to the next talk.
Okay.
Paul Barham from Google Brain. So you keep replicated weights, presumably because if you didn't, the stale weight problem would be just like asynchronous training. And in asynchronous training, if the gradients are quite sparse, that works reasonably well. So I was wondering if you explored in your paper how, as you change the batch size, the sparsity of the gradients changes, and whether you can get away with not keeping replicated weights. And a sort of corollary of that is, if your gradient terms are quite sparse, it's cheaper to keep those than to keep multiple copies of the weights. So I was wondering if you...
Yeah, I'm not sure I fully caught the question. But was your question about what if we try to integrate PipeDream with or we try to use gradient compression and techniques like that, or?
Well, the question was, did you explore whether you could get away with using asynchronous training or gradient compression instead of keeping lots of copies of the weights?
Yeah, so we didn't use that, and we didn't explore that. It's definitely interesting future work, trying to figure out when one should do gradient compression. and like maybe like we can like make the PipeDream optimizer like aware of like compression, and we can figure out when compression is a good idea. But we haven't like explored that yet. Yeah. Thanks. All right. Awesome. Thanks.